Combined heat and power. Welcome to Combined Heat and Power. The session introduces the concept of cogeneration, showcasing how CHP systems efficiently produce both electricity and heat from a single fuel source. Let's explore their components, technologies, and benefits for energy optimization. Topics to be covered. In this presentation, we will cover the definition of cogeneration, also known as combined heat and power or CHP. We will explore how CHP systems produce both electricity and useful heat from a single energy source, utilizing fuels like natural gas, coal, and biomass. We will also discuss the various technological approaches used in cogeneration, such as steam turbines and gas turbines. Lastly, we will evaluate CHP plants by considering key factors like efficiency, fuel availability, cost, and environmental impact. Combined heat and power system. CHP systems generate both electricity and thermal energy from a single fuel source, significantly increasing overall efficiency. Instead of wasting heat produced during electricity generation, CHP captures this heat for heating or industrial processes, maximizing energy use and reducing costs. Cogeneration. Cogeneration, or CHP, involves the simultaneous production of electricity and heat from a single fuel source. This dual production enhances efficiency, as the heat generated during electricity production is repurposed rather than wasted. Heat engine. Heat engines play a crucial role in converting thermal energy into mechanical energy, which is then used to generate electricity. In CHP systems, heat engines capture waste heat, thereby increasing overall system efficiency and reducing fuel consumption. Power station. Power stations are facilities that generate electricity, typically using fossil fuels or renewable energy sources. In CHP systems, these power stations capture and utilize waste heat, providing additional energy for heating or industrial processes, thereby enhancing overall energy efficiency. Absorption chiller. Absorption chillers are innovative systems that use heat instead of electricity to produce chilled water, commonly for cooling buildings. In CHP systems, they make use of waste heat, enhancing energy efficiency while reducing cooling costs. Spark ignition and compression ignition engine. Spark ignition engines utilize a spark plug to ignite the fuel, whereas compression ignition engines rely on high pressure for ignition. Both engine types are utilized in CHP systems, especially for on-site power generation, contributing to energy efficiency. Waste incinerator. Waste incinerators burn waste materials to generate energy. In a CHP system, the heat produced can be used to create steam for electricity generation and additional heating. This provides the dual benefits of effective waste management and energy production. Natural gas. Natural gas is a preferred fuel for CHP systems due to its high efficiency, lower emissions, and widespread availability. It powers turbines or engines that generate both heat and electricity, maximizing the energy output of a single process. Diesel fuel. Diesel fuel is commonly used in CHP systems, particularly in regions lacking a natural gas supply. While not as environmentally friendly as natural gas, diesel is a reliable option for generating both power and heat, especially in remote or emergency situations. Propane. Propane serves as an alternative fuel in smaller CHP systems, particularly in rural or off-grid areas. It is cleaner than diesel but less efficient than natural gas, making it suitable for localized energy solutions where natural gas is not available. Coal. Coal-fired CHP plants are designed to capture waste heat, which enhances efficiency. Although coal is a high-carbon fuel, its use in CHP systems can reduce environmental impact compared to traditional coal power plants by maximizing energy output. Wood and wood waste. Biomass, such as wood and wood waste, is a renewable fuel option for CHP systems. It provides a sustainable energy source, particularly for industrial applications, helping to decrease dependence on fossil fuels. Cycle of biomass energy. Trees and plants. Trees and plants absorb carbon dioxide, $2, from the atmosphere through photosynthesis, storing it in their biomass. Biomass, the organic matter from trees and plants is collected as biomass, which can include wood chips, wood pellets, and agricultural residues. Biomass power plant, the biomass is burned in power plants to generate electricity. CO2, carbon dioxide, $2, is released into the atmosphere as a byproduct of burning biomass. Wood products. Trees and plants are also used to create wood products like furniture and paper. Biogas. Anaerobic digestion of biomass can produce biogas, which can be used as a fuel source. Rankine cycle. The Rankine cycle is a thermodynamic cycle that converts heat into mechanical energy, commonly utilized in steam turbines. In CHP systems, the waste heat generated from the Rankine cycle can be repurposed for additional heating applications. Otto cycle. The Otto cycle describes the internal combustion process in spark ignition engines, which are frequently used in smaller CHP units. This cycle enables the generation of both electricity and useful heat, thereby increasing overall energy efficiency. Brayton cycle. The Brayton cycle is another thermodynamic cycle used in gas turbines. In CHP systems, this cycle generates electricity while capturing waste heat, which can then be utilized for heating, further optimizing energy use and overall efficiency. Cogeneration plant. A cogeneration plant is a facility designed to produce both electricity and heat. It employs waste heat recovery systems to capture energy that would otherwise be lost, delivering higher efficiency and cost. The topping cycle. Next, let's explore the topping cycle CHP system. This system works a little differently. It starts by feeding a fuel like natural gas or biomass into a prime mover, which could be a turbine or engine. The fuel's energy is converted into mechanical energy, which drives a generator to produce electricity. But we're not done yet. The exhaust gases from this process, which still carry thermal energy, are sent to a heat recovery unit, where they're used for heating or hot water. Think about the efficiency here. One fuel source is creating both electricity and thermal energy. The bottoming cycle. Welcome to the bottoming cycle combined heat and power, CHP, system. Imagine you're in an industrial facility, like a cement plant or a steel factory. These operations generate a lot of waste heat, but what if we could capture that and make use of it? That's exactly what the bottoming cycle does. In this system, a heat recovery unit captures the excess heat produced by the plant process, whether it's from cement manufacturing, steel production, or glass making. This heat is then used to drive a turbine, generating electricity without using extra fuel. Combined cycle CHP. Now, let's dive into a more advanced system, the combined cycle power plant. This system combines two types of turbines, a gas turbine and a steam turbine. First, a gas turbine burns fuel to produce mechanical energy, generating electricity. But the real magic happens with the waste heat. This heat is captured by a heat recovery steam generator, HRSG, which turns water into steam. The steam then powers a steam turbine, generating even more electricity. You can see how this makes the system far more efficient than just using a gas turbine alone. After generating power, the steam is cooled and reused, closing the loop. By now, you should see how combining these two cycles maximizes power generation and minimizes fuel consumption. Electric generator. Let's zoom in on a critical component of any CHP system, the electric generator. This device converts mechanical energy from engines or turbines into electricity. Whether it's a gas, diesel, or even a renewable engine, the generator is at the heart of electricity production in CHP systems. It can supply power directly to the facility or send excess power to the grid. In any CHP system, the generator must be reliable and efficient, because it's responsible for meeting both on-site power needs and any additional energy demands. Diesel engine. Let's talk about diesel engines, which are commonly used in CHP systems for their robustness and efficiency. They're especially valuable in smaller systems or areas that don't have access to natural gas. Diesel engines generate both electricity and heat, making them useful in facilities that need uninterrupted, local power. Can you think of situations where this kind of backup power would be crucial? While they emit more pollutants compared to natural gas engines, they're still highly efficient under heavy load and have the advantage of being reliable. Natural gas engine. Now, let's consider natural gas engines. These are favored in CHP systems for their cleaner emissions and high efficiency. Unlike diesel, they have a better environmental profile, producing fewer pollutants. They're perfect for high-usage facilities, like hospitals and hotels, that need both power and heat. Their quick response to fluctuating power demands makes them reliable. Steam turbine. Moving on to steam turbines, these are often used in combined cycle CHP systems to harness the power of steam. The steam, which is generated by waste heat, drives the turbine and generates additional electricity. Steam turbines are incredibly reliable and can handle a wide range of steam conditions. Gas turbine. Let's now look at gas turbines. These turbines are powered by fuels like natural gas and are highly efficient at converting fuel into mechanical energy to generate electricity. The exhaust gases are hot and ready to be used for additional power generation in a combined cycle system. Gas turbines can scale up to meet large demands, and they integrate well with steam turbines, enhancing overall system efficiency. Microturbine. Microturbines are compact and versatile, making them ideal for small-scale CHP applications. They can run on natural gas or biogas, producing both power and heat for small buildings or industries. Their low maintenance needs and ability to work in various settings make them especially appealing for decentralized energy production. Water treatment plant. Water treatment plays a vital role in CHP systems. When using steam and heat, it's crucial that only high-quality, treated water is used to prevent scale buildup and corrosion in boilers and turbines. Without proper water treatment, the system's performance could decline, and maintenance costs could rise. Air scrubber. Air scrubbers are used to remove pollutants from exhaust gases in CHP systems. They filter out harmful particles, sulfur compounds, and other pollutants, helping the system meet environmental standards. Without scrubbers, emissions could contribute to air quality problems and potentially harm the local environment. Ratchets. Ratchets are mechanical devices used in CHP systems to control the movement and rotation of parts like turbines. They ensure that turbines don't backspin when the system is turned off or the load changes. This helps prevent damage and ensures smooth operation. Utility supplier. Utility suppliers play a key role in CHP systems. They manage the flow of energy between the CHP system and the local grid, ensuring that excess power is exported when available. Utility suppliers help balance on-site generation with grid demands, ensuring stability in the broader steam generator. Steam generators are essential in any CHP system that uses steam. They heat water to produce steam, which can then drive turbines for power generation. The steam can also be used for heating and industrial processes. This dual-purpose energy maximizes fuel efficiency, which is a big win for industries that need both electricity and heat. Slide 16. Heat recovery steam generator, HRSG. HRSGs capture waste heat from gas turbines and turn it into steam, which is used for additional power generation. By recycling exhaust gases, HRSGs reduce fuel consumption and emissions. Duct burner. Duct burners are used in the HRSG to add extra heat to the exhaust gases, boosting steam production. This increases the CHP system's power generation capacity, especially during peak demand. Electrical utility grid. The electrical utility grid connects CHP systems to larger power networks. This connection allows CHP systems to export surplus power and support grid reliability, especially during high demand periods. By balancing the output from CHP with grid power, this system helps stabilize energy supply. Naphtha. Naphtha is an alternative fuel used in some CHP systems. It's energy dense and can be used when natural gas is not available. However, it does have higher emissions, so careful management is required. LPG. LPG is a cleaner burning alternative to diesel and is often used in CHP systems for its versatility. It produces fewer emissions and is a good option where natural gas isn't available. Biogas plant. Biogas plants convert organic waste into biogas, which can then be used in CHP systems. This renewable energy source reduces landfill waste and contributes to a cleaner, more sustainable energy system. Fuel cell. A device that efficiently converts chemical energy into electrical energy through an electrochemical reaction. As seen in the images, the fuel cell stack is composed of multiple layers, including bipolar plates and membrane electrode assemblies, designed for optimal energy conversion. Fuel cells are widely used in electric vehicles, power generation, and portable devices due to their high efficiency and eco-friendly operation, emitting only water and heat as byproducts. Phosphoric acid fuel cell, PAFC. Let's dive into the phosphoric acid fuel cell, PAFC, one of the most reliable fuel cell technologies used in combined heat and power systems. PAFCs are known for their stability and long-term operation. They use phosphoric acid as the electrolyte, which allows them to operate efficiently at moderate temperatures, typically around 150 to 200 degrees Celsius. The process generates both electricity and heat, making them ideal for commercial and industrial applications that require continuous power. PAFCs have a proven track record, offering reliable energy production with low emissions. Molten carbonate fuel cell, MCFC. Next up, we have the molten carbonate fuel cell, MCFC. These fuel cells operate at much higher temperatures, typically around 650 degrees Celsius. This high temperature allows them to achieve high efficiency, making them ideal for large-scale CHP systems. MCFCs can run on a variety of fuels, including natural gas and biogas, which further enhances their versatility. The molten carbonate electrolyte makes them capable of converting fossil or renewable fuels into both power and heat, while maintaining low emissions. MCFCs are particularly suited for industrial applications that require substantial power generation. Solid oxide fuel cell, SOFC. Finally, let's explore the solid oxide fuel cell, SOFC, which is known for its impressive efficiency and durability. SOFCs operate at very high temperatures, typically around 800 to 1000 degrees Celsius. These fuel cells use a solid oxide electrolyte, making them highly efficient in converting fuels like hydrogen, natural gas, or biogas into electricity and heat. Due to their high output and long lifespan, SOFCs are well suited for industrial-scale applications that require continuous power. They are also ideal for applications where reliability and clean energy are critical. With the potential to utilize a variety of fuels, SOFCs offer a flexible solution for the future of energy. Thank you for your attention. For more details, please contact TSD Office Engineering GHG. We appreciate your interest in ESG initiatives.